Imagine standing on a shoreline at night. You can see lights across the water. Faint, distant, almost unreal. You know there's land over there, cities, mountains, entire civilizations. But the ocean between you isn't a few miles wide. It isn't a few hundred. It's an ocean so vast that even light, the fastest thing in the universe, takes millions of years to cross it. That's where humanity stands right now, looking at the next galaxy and realizing we will never reach it. Not in 1,000 years, not in 1,000,000, possibly not ever. Our nearest galactic neighbor is the Andromeda galaxy. It sits about 2.5 million light-years away. In cosmic terms, that sounds close. In reality, it is a distance so extreme it breaks the way your brain understands space. And the reasons we will never reach it aren't about funding. They aren't about politics. They aren't even about engineering. They're about scale, about physics, about the architecture of the universe itself. Tonight, we're going to walk through that ocean. We'll start with distance, because almost everyone underestimates it. Then we'll test our fastest machines. Then we'll confront the absolute speed limit of reality. And finally, we'll face the part no one likes to talk about. Even if we could survive the physics, we wouldn't survive the time. Let's begin with something manageable. The moon is about 384,000 kilometers away. Light gets there in 1.3 seconds. Humans did it in 3 days. Now stretch outward to the edge of our solar system. The Voyager probes have been traveling since 1977. Nearly 50 years. They have just barely entered interstellar space. Now zoom out further. The Milky Way itself is about 100,000 light-years across. Our entire galaxy, hundreds of billions of stars, is a single island of light in a dark ocean. And that ocean contains trillions of other islands. The closest large one? The Andromeda galaxy, 2.5 million light-years away. Let's make that real. If the Milky Way were shrunk to the size of North America, Andromeda would be another continent across an entire Earth-sized globe. But that analogy still fails, because continents are connected by oceans you can cross. Galaxies are separated by vacuum so deep it makes interstellar space look crowded. At the speed of Voyager 1, about 61,000 kilometers per hour, reaching Andromeda would take over 44 billion years. That's more than 3 times the current age of the universe. Even our fastest spacecraft ever built, the Parker Solar Probe, would need tens of billions of years. Longer than stars live, longer than galaxies remain stable. The journey wouldn't just outlast you, it would outlast humanity. You might think, so we just need to go faster. That's where the second wall appears, the speed of light. Nothing with mass can reach it. This isn't a technological limitation. It's a fundamental rule described by Albert Einstein in his theory of special relativity. As an object accelerates toward light speed, the energy required to push it faster increases exponentially. Approach the speed of light and the required energy approaches infinity. Infinity. Not a large number, a boundary. Even if we could build a spacecraft that travels at 10% of the speed of light, something far beyond current capability, the trip to Andromeda would take 25 million years. 25 million. When our ancestors 25 million years ago were climbing trees. Civilizations rise and fall in thousands of years. Languages mutate beyond recognition in centuries. And we're talking about a voyage longer than the entire existence of our species. But maybe we don't need to go that fast. Maybe we invent something radical. Warp drives, wormholes, shortcuts through space-time. The warp concept most people reference was mathematically described by Miguel Alcubierre. On paper, it allows space itself to contract in front of a ship and expand behind it. But here's the problem. It requires exotic matter with negative energy density, something never observed, and energy requirements comparable to planetary mass converted entirely into fuel. Even if that problem were solved, there's another one waiting. Intergalactic space is not empty. It contains diffuse hydrogen, stray particles, and high-energy radiation. At relativistic speeds, even a microscopic grain of dust becomes a projectile with explosive force. A speck the size of sand would hit with the energy of a bomb. Over millions of years, the cumulative damage becomes inevitable. But let's assume we solve shielding, we solve propulsion, we solve energy, we solve impact protection. There's still time. At 10% light speed, 25 million years. That means a generation ship lasting not centuries, not millennia, but geological epochs. Human history as we know it spans about 5,000 years. Recorded history is a blink. Empires collapse in centuries. Political systems fracture in decades. Now imagine maintaining social stability for millions of years inside a sealed spacecraft. No planet, no external resources, no possibility of rescue. Even the concept of a mission would erode. After 10,000 years, the origin story becomes myth. After 100,000, language transforms beyond recognition. After 1,000,000, the purpose is gone. And then there's biology. Cosmic radiation exposure over millions of years, genetic drift, mutation accumulation, closed-loop ecosystems destabilizing, artificial gravity systems needing maintenance for time spans longer than multicellular life has existed. Even stars are not eternal. In 25 million years, stellar neighborhoods shift. Galactic structures evolve. The Andromeda galaxy itself is moving toward us at about 110 kilometers per second. In roughly 4.5 billion years, the Milky Way and Andromeda will collide. Not in a catastrophic explosion, but in a slow gravitational dance merging into a new galaxy. Ironically, Andromeda is coming to us, and it will arrive long before we could ever go to it. So where does this leave us? The truth is uncomfortable. Intergalactic travel is not just hard, it is fundamentally misaligned with biology, physics, and time. The distances between stars challenge engineering. The distances between galaxies challenge existence itself. Even if propulsion breakthroughs occurred tomorrow, even if we harnessed fusion, even if antimatter drives became routine, the speed of light remains non-negotiable. And at that speed, the trip still takes 2.5 million years. No civilization has ever lasted that long. No species has maintained technological continuity on that scale. And even if one did, the universe itself evolves. Galaxies move, stars explode. Dark energy accelerates cosmic expansion, increasing distances over time. In fact, on sufficiently large scales, galaxies are receding from us faster than light due to the expansion of space itself. Not violating relativity, but stretching reality. Meaning some galaxies are already permanently unreachable, even in principle. So when we ask why we will never reach our next galaxy, the answer isn't pessimism, it's proportion. We evolved on a small, rocky planet orbiting an average star in one spiral arm of one galaxy. And yet we can measure galaxies millions of light years away. We can map their motion. We can analyze their spectra. We can predict their collision billions of years in advance. Our bodies will never cross the intergalactic void, but our understanding already has. Maybe that's the real story. Not that we are trapped, but that the universe is staggeringly large, and we are a species capable of comprehending scales we will never physically conquer. The ocean between galaxies is real, cold, silent, unforgiving. But the fact that we can stand on this shore, look across 2.5 million light years, and understand what lies there, that matters. Because sometimes the greatest journey isn't traveling the distance, it's grasping how vast it truly is. And that is something we've already done. I really hope you enjoyed this video. If you're curious about the limits of human space travel, consider subscribing. I'll see you in the next one.